Okay, so example 2 for continuity. Is the function f of x continuous at x equals 1 where f of x is a piecewise function, so the left piece is x plus 1 when x is less than 1, and the right piece is x squared plus 1 when x is greater than 1. Alright, so they're asking for whether a function is continuous or not, so we got to prove these three conditions. So the first condition is f of a is defined. So is f of 1 defined? Well, it is defined because here when x is less than or equal to 1, the y value is x plus 1. So we could just plug 1 in for the x and we'll have 1 plus 1, which is equal to 2. So the first condition passes. F of 1 is defined. Now, what's the second condition? We have to prove that the limit as x approaches 1 of f of x exists. And how would we do that? We got to prove that the limit approaches the same value from both sides. So on the side here, I'm going to make a table of values for this, and then I'm going to graph it so we can see whether the limit exists or not. So let's start off with this left piece. So when x is less than or equal to 1, we got a table of values, and the y value will be x plus 1. So let's start off with 1, 0, negative 1, negative 2. So when x is 1, y is 2, then y is 1, then y is 0, and then y is negative 1. All right, now what about the right piece of this function? So x, and then the y value will be x squared plus 1. So let's pick some x values after 1. So 2, 3, 4. So plugging these in, you'll get 2, 5, 10, 17. And if we roughly graph this function, so let's graph this left piece first, and let's start off at 1. At 1, we have a y value of 2, and it's defined at 1, so there would be a dot at 2. And then at an x value of 0, we have a y value of 1. Then at an x value of negative 1, we have a y value of 0. And then at negative 2, we have a y value of negative 1. So this would just be a line. Doesn't look like a line too much, sorry about that, but it's just a straight line, right? X plus 1. Now, what about this right piece here? So at an x value of 1, we also have a y value 2. It's not defined there, but notice how the y value is the same as the left piece. So we can add it on to the dot. Then at 2, we have a y value of 5. And then at 3, it's a y value of 10. So that ends up being just a parabola, right? And it's just going up. So we can tell that the function is continuous at 1. It hits 2 on both pieces. And so the limit exists from both sides. As x is approaching 1 from the left side, the y value is 2. And as x is approaching 1 from the right side, the y value is 2 as well. So the limit exists as x approaches 1 of f of x, and it's equal to 2. So the second condition passes, and then the third condition that we have to prove is that the limit as x approaches 1 of f of x is equal to f of 1. And notice how both of these are the same. So the limit as x approaches 1 of f of x does equal f of 1, and they both equal 2. So all three conditions pass, so therefore f of x is continuous at x equals 2.